Should I give him a call then? कॉल करें उनको?
हाँ, give him a call.
Can you hear me?
Yeah, I can hear you.
Okay.
So,
Yeah.
Hi, Naveen.
Hi.
How are you?
I'm good.
After a long time.
Yeah, I
Hmm.
see a lot after a long time.
Hmm. Though still
so
I
working.
can you try to share your file slides?
Yeah, we can share this. Hmm.
uh, we'd also like to record this. I hope you have no issue with that.
Yeah, it is fine. Yeah, yeah.
Uh-huh.
Hmm. I don't see. I don't know why.
There is a green arrow. This
No, I
arrow
saw
in a
that,
green
but
background.
I have in Google share this PPT file, but I don't see that. I don't know why. Hmm.
No option.
No, the green arrow I clicked, but usually it shows that particular file, but I don't see now.
Uh,
Otherwise, I can send the PDF and you can share from
uh,
there. Let me try again.
you try again, and then others will do that.
How to stop that again? Try. Yeah, I don't see stop option also. Okay, so maybe you make me host or something.
You are currently a host.
Mm-hmm. Mm.
You can share your whole screen or a
Mm-hmm.
particular application also.
Now I see. Okay.
Is it working?
Can you see?
Yeah. See that.
You can
Yeah,
see
we can see. And please change one of the slides so that we can see that whether. Yeah, yes.
Okay. Mhm.
And I would request you one more thing to do, that you can see probably three dots on your screen, on the top of your screen.
Mhm.
And if you click there, you will be able to see something called that disable annotating by others.
Uh, I clicked that three dot. It says view profile, mute my audio, adjust background, all these things, but I don't see disable.
Uh, at the top, there is three dots are there. Means only speaker can disable annotating, others stop annotating this. Otherwise, other people can annotate on your slide. So that option you will get it on the top. There is a three.
Yeah,
This
there is this three dot and there is mute on the side. So I don't. Uh, I don't see that.
okay. Anyway, let's.
So who are the audience? Students or only faculty or?
Mostly students from various institutions all over India.
Okay. Any BTech student from LNMIIT or?
Means they registered yet. Right now, I can't see them right now, but probably they will join.
Mhm.
We can wait for a few minutes and then can start.
Yeah. You can wait for 2 minutes and then you can.
So currently you are living at Bhubaneswar or where?
Yeah, right.
Right now you are in Bhubaneswar.
Mm.
I have not went to Bhubaneswar for a long time, so sometime I have to visit. Recently, Ajit also gave a talk here.
Online or
So he
physical?
in online.
Okay.
And once Ajit visited Jaipur, I think 2 years back that time we met.
Mhm.
Uh, so sometime I will invite you also so that we can meet again.
Mhm. Are there any guest house available there?
Yeah, guest house is there.
Mm. Okay. Maybe I can.
Yeah, sometime even if you feel like visiting Jaipur for some reason, you can also tell me. We can arrange a talk here.
Maybe, yeah, if I visit, I can plan with my family
Uh,
also.
yeah, we can host you.
Yeah, Jaipur, I have never been. I don't.
Oh, then you should come once at least.
Yeah.
Okay, Navendra, you can start now.
Okay, so I'm very happy to introduce Professor Arun Kumar Poti for today's talk. So Professor Poti is a renowned Indian physicist. He's he's a leading authority in quantum information, quantum computation, and foundation of quantum mechanics. And he is working on this field, as far as I know, for at least more than 3 decades almost. And he started working in these fields when very few people used to work. And in his brief biography, he had a MSc degree from Berhampur University and then PhD from University of Bombay. Then he started his career at BRC. Then he held academic positions in Institute of Physics Bhubaneswar, HRI Allahabad, IIIT Hyderabad, and he is also associated with many centers, Center for Quantum Technology at KITS University. Then he is also founding director of Quantum Ecosystem and Technology Council of India. So he has many pioneering contributions on no deletion theorem, no hiding theorem, no masking theorem, etc. And he received many honors, including Indian Physical Society Award for Young Scientist, Indian Physics Association Young Physicist Award, Shamanta Chandrasekhar Award, J.C. Bose National Fellowship, etc. And moreover, I have a privilege to have him as my teacher during my early PhD days. He taught us quantum mechanics that time, and it was mostly oriented towards this quantum communication and quantum computing direction. And with that personal anecdote, I request Professor Poti to start with his presentation. And thank you, Arun, for accepting this our request. And we are really privileged to have you here with us.
Thank you, Dr. Nabendu, and Dr. Vishwas also for inviting me to deliver this talk via online mode. Even though you have been inviting for some time, but I couldn't find time. But finally, I could make it, so I'm really happy to do this today. And so today, what I'm going to talk about is this new emerging area on quantum computing, which is in quantum technology, which is one of the most talked about subject in recent times. And all of you may know that not only academicians are interested in this field, but also government has invested a huge amount of money in this under National Quantum Mission, and private companies, they are also investing hugely, starting from Google, IBM, and hundreds of startups, or maybe more than several hundreds also. So I will try to give a brief overview of this field and why this field is exciting, and what are the futures of this field, and how this is going to change the future of computing and communication and whole of new technology. Okay, so with that, let me start. Okay, so when we talk about quantum technology, basically we have in mind three themes. One is quantum computing, one is to do with quantum communication, and quantum metrology and sensing, and quantum hardware and materials. And in fact, if you see, National Quantum Mission has invested heavily under these four thematic hubs, and many researchers from India, they are involved in this, and they're contributing in a significant way. So in my talk, I will try to cover these first two things, quantum computing and quantum communication. I will not have time to touch about these two topics. So I will try to focus mostly on this computing and communication side. Okay, so before I go to quantum computing side, we all know what is classical information. So whenever you talk about classical information, you store information in strings of bits, and any given time you have a classical bit which can be in 0 or 1, and that's how you constitute or regard this as a basic unit of classical information. And all present in the computer, whether your laptop or mobile or even supercomputer, basically they store information in strings of bits. And what you have in mind is basically you store information on transistors, switching between on and off state. If it is on, you say 0. If it is off, you say 1, and so on. And these two distinct positions refer to 0 or 1, as I said, and that represent two possible state of a classical bit. And then you do various tasks according to classical laws of physics. When I say classical laws of physics, basically It could be, you can use Newton's law or Maxwell's equation and, classical optics and things like that. But you never find in combination of 0 and 1 in classical world. Then what happened was Richard Feynman, one of our great physicists, all of you know, that he started asking the following question in 1982. He raised this question that what will happen if you store information in two distinct state of a quantum object? And why he asked this question? Somehow he realized, he had a great intuition that if you try to simulate complex quantum system on a classical computers, he thought that that would be very, very inefficient. Then why not use quantum system to simulate quantum system itself, So that's how, he tried to reason out, and he said, okay, so what will happen if you store information in quantum system? But then he did not pursue really seriously at the time. A few years later, in 1985, David Deuss, he took this idea very seriously, and he single-handedly tried to develop the whole theory of quantum computing. And the only guiding principle to him was the so-called quantum superposition principle, because if you use that, then you can have a new way of storing information which you don't see in classical world. And quantum mechanical superposition principle allows you a new way of storing, manipulating information. And quantum computer are basically any device that you can think of or you can design that performs computation using principles of quantum theory, the ultimate theory of nature. So you can say the original idea of quantum computer would actually came due to David Deuss in 1985. And if you compare classical versus quantum computing, you will encounter a few new concepts like qubits, superposition, entanglement, quantum gates, and so on, which you don't see in classical world. And why quantum computing matters? Because there is a lot of hope that quantum computer can solve certain complex problems exponentially faster than classical computer, or even supercomputer also. And that could revolutionize fields like computing, quantum chemistry, drug discovery, material design, machine learning, and artificial intelligence. And this will open a new frontier. This will open up new frontiers in computing and scientific discoveries in future. So coming to quantum bit, as I said, let us try to distinguish these two notions like classical bit and quantum bit. Classically, I said that if any classical bit can remain in 0 or 1. Now, if you think of a quantum system and identify two distinct states like spin up, spin down state, then you can say if it is spin up, it is 0, if it is spin down, it is 1. Okay. But then I know that the quantum system can remain also in a linear superposition of this spin up and spin down state. Like, like state of electron, So electron spin state can be in a linear combination of spin up and spin down state with some complex amplitude alpha and beta. We know that, right? So now if you translate this to logical language, then you will have a state which looks like alpha 0 plus beta 1. And this is basically your quantum bit, because your logical state at any given time is not only 0 or 1, but it is both 0 and 1 with some amplitude alpha and beta. So this somehow trying to tell you that there is some kind of inherent parallelism that comes into play, and that is basically responsible for new type of computation, what we are trying to talk about, this quantum computation. And you can store information like this alpha 0 plus beta 1, not only in electron spin, you can also store same information in photon polarization, you can store in two atomic levels, or you can store in any quantum system by identifying two distinct quantum states. Okay, could be spin, could be polarization, could be energy level, could be any other degrees of freedom. You can identify, and then you can store this information. Now, pictorially, you can see that if I'm a spin is up, then I say it is 0, if down it is 1. And this is basically a state which looks like superposition state, both alpha up plus beta down. And but if you do a measurement, we know that your state will collapse to one of the eigenstate. You will get only two distinct outcomes. So you see a quantum bit, which is truly a superposition of alpha and beta, when alpha up plus beta down, that potentially has a large amount of information, because if you don't know what is alpha and beta, this could be alpha and beta, they are complex numbers. That means you can identify with real numbers. You can represent the same quantum state with real numbers also. Then there are potentially infinite number of possible states you can identify from this superposition. But then by doing measurement only, you can extract only two possible outcomes. That means you can extract only one classical bit. So this is kind of clear distinction between classical and quantum bit. I will talk more in next few slides. Now, if you go to two quantum bit, let's see what happens. Now, we know that two classical bit can be in any one of these four logical states, like 0, 0, 0, 1, 1, 0, 1, 1. And if I try to do same thing with quantum system, I can do that. That means I can also think of two electron spin, like up, 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 down, down, up, and down, down. But then, because of superposition principle, I can have a quantum bit. I can have a two quantum bit which can remain simultaneously in all four logical states. So that is the beauty of superposition principle. Now, if you go to n quantum bit, you see how this, how vast this Hilbert space grows actually. So in classical computer, your n bit can be at any time, can be in one of these two different possible logical states. But your quantum computer with n qubit will have all those exponential number of logical states at any given time. So the Hilbert space grows exponentially with the number of qubits. Now, for n equal to 300, this is roughly 10 to the power 90, which is more than the number of atoms in the known universe. So how vast this really grows, you can see from here. So quantum computer trying to take this advantage of this exponential number of logical states, which basically leads to this massive parallelism. And this massive parallelism is only possible with quantum computer. You don't see it classical computer. Now, what can you do? So the question, what can you do with quantum computer? You can do many things. Now, technological revolution from quantum computers may allow you to solve problems that are currently too complex for classical supercomputers. In early days, like 1994 to 96, 98, around that time, only handful of algorithms have been discovered, like source algorithm, reverse algorithm, and Deutsch algorithm. And source algorithm made this field really, give a big boost to this field, because that tried to show that quantum computer can be used for factorization in exponential faster than classical computer. And reverse algorithm tried to show that you can do database search, like trying to find an item from say n entries and a quadratic number of steps, basically, and quadratic improvement. That means classically, if you take n steps, quantum mechanically you can do in square root of n steps. Now, this Deutsch algorithm tried to show that there is a certain kind of computational task, like deciding nature of some function, which takes classically again exponential number of steps, but quantum computer can do it just with one query, one step. So that's the beauty of this massive parallelism, which is revealed by this Deutsch algorithm. This last one is not of much use, just it is just a illustration how powerful is quantum computer, but not a practical application. But these two have been found, wide range of applications. Now, over last over last 10 years or so, we have seen a new trend, and that trend is not only to develop algorithm or discover theory of algorithm, but to build quantum computer, and that has been the race of 21st century. And this is a very challenging and ambitious task. And why this is so? Because once you have quantum computer, that can potentially revolutionize future computing abilities, and that can lead to plethora of useful applications starting from healthcare to defense, finance, chemistry, material development, software debugging, aerospace, transport, and many more things. And as I said, the speed and power of quantum computer actually lie in the fact that quantum system can be in multiple quantum states that only occur at a quantum level. Therefore, we need to bring quantum computing to commercial reality, and that need extraordinary team to put their efforts. And that is why you see that all the big companies, starting from Google, IBM, Microsoft, and a host of other companies, trying to invest heavily in this quantum computing and quantum technology side. Okay, now if you see the timeline for the global race, you see that just exactly 10 years back, IBM started this platform with 5 qubit. Then within a year, they went up to 17 qubit. And within 3 years, they went up to building about 65 qubit. Again, within a year, they went about 127 and so on. So you see how the number of qubit they could design really grows. And in 2019, there is a big news that Google claimed that somehow quantum computers showed the supremacy in the sense that they could do something, some task with 54 number of qubit, which they could solve in 200 seconds, whereas the best supercomputer may take 10,000 years. And in 2020, Chinese team, they built another platform that is even they claim that is even more faster than Google's quantum processor, even in fact 10 billion times faster than Google's processor. And with their device, they could do some tasks. Again, don't worry about what exactly they did, but basically a proof of principle that they showed that if you do that particular task, they could solve in 200 seconds, whereas world supercomputer will take approximately 2.5 billion years to do the same calculation. That shows a clear example of quantum supremacy by your quantum computers. And last year, Microsoft claimed to build 8 qubit processor, and IBM they had claimed about 1386 number of qubit. Within that processor, they have also quantum communication link and so on. And very latest news is just a few months back, towards the end of last year, that is this Harvard and MIT group, they built about 3,000 quantum bit, and they could run the quantum computing algorithm for more than 2 hours. And in same month, this Caltech group, they built about 6,100 number of ultra-core cesium atom quantum computer. Again, this is the record-breaking, atomic qubit that this group has built. So progress is really fast over the last 10 years, and maybe next 5 to 10 years, one will have a really full-fledged quantum computer. So now to build, to build quantum computer, not easy, obviously. Otherwise, people might have already bought, they have already, many companies would have already built this large-scale quantum computer. A lot of challenges, but few of the challenges are the following: that is to do with scalability, that is all the present day quantum computer, whether 3,000 qubit or 6,000 qubit, they are basically noisy intermediate scale quantum computer. Why they are noisy? Because all these quantum computers, they are not error free. Okay. And the second thing is you have to worry about decoherence and noise, because once you scale up, the quantum bits, they may try to interact among themselves, they may try to interact with the external world and so on. And that lead to decoherence, and your qubit lose the coherence and so on. So how to improve this qubit stability? That is second challenge. Third challenge, error correction. That means you have to build your quantum computer which are fault tolerant. And to build quantum computer which are fault tolerant, you have to encode your logical state in many physical state. That means to have, say, to build one logical state, you have to encode maybe 100 or maybe several hundred, physical state. So that really gets multiplied. Means if you have, let's say, 1,000 logical qubit which are fault tolerant, you have to have maybe million physical qubit. So that is a real challenge. And not only that, you need to also have algorithm development. You need to develop new quantum algorithm and which can be implemented and which will demonstrate more practical quantum advantage compared to classical supercomputer. So that is still an active area of research, and a lot of development has happened over last 10 years or so, or maybe last 10 to 15 years. But still a lot of challenges, lot of open questions are still there. Because one thing one should keep in mind that it is not true that quantum computer can solve everything faster compared to classical computer. Quantum computer can do everything that classical computer can do, but whether something can be done faster than classical computer, it is not obvious, not very clear. So wanted to see, wanted to prove and demonstrate that indeed some particular task can be solved faster in a quantum computer compared to classical computer. So that is a quite challenging task. And that is why you need to develop new algorithms, Okay, now I will go to quantum communication side and a few other things. Before I go to quantum communication, I have to tell you about the notion of entanglement and why they are interesting and what you can do with quantum entanglement. Now, this notion of entanglement we are using over last 30 years or so, but it was already discovered by Schrodinger in 1935, many years back. And in same year, Einstein and Podolsky-Rosen, they tried to use these entangled states, and they realized that this kind of state displays strong correlation between space-like separated particles, and they display some kind of spooky action. And now we are using this spooky action for quantum computation and quantum communication. Even though this was known for many years, but people did not really appreciate the use of entanglement. Most of the papers you will see between 1935 to 1966 till the work of John Bell, mostly they had to worry about how to resolve this Einstein-Podolsky-Rosen paradox and so on. And because what they did was, in this paper they tried to use entangled state, and they revealed that they have this kind of spooky action, and they tried to argue that quantum theory is incomplete. I'm not going to explain about the PR paper, but because that is quite deep and subtle paper, I mean, that itself will take 1 hour to to tell in detail. But basically, Einstein, as you, some of you may know, that he was a person of very strong belief that world is local and real. Local means whatever I do to my particle in my lab, that should not influence the particle in your lab, okay? And real, it means any attribute that your quantum system possesses is independent of observation. That means whether I look at or you look at, the attribute will not change. That means there is some element of reality. So using these two naive notion of locality and reality, he tried to use entangled state and argue that quantum theory is a theory which is not a complete theory. He was very much hopeful that maybe someday, one will discover more fundamental description of nature, and then quantum theory will be a kind of social case of this larger theory. But it was John Bell who tried to disprove Einstein's belief that no, quantum theory cannot respect locality and reality. So you have to drop one of the condition, and that is why you see that entangled state display highly non-local correlation and so on. Okay, but that is another story. So I'm not going to tell about all those stuff, but I think this is wanted to appreciate how this notion started. Now what exactly is quantum entanglement? If you have a quantum system that consists of more than 2 or more number of particles, then your quantum state or quantum system can be found in a strange kind of state. Basically, think of a two-particle system, and your joint wave function or state vector of the composite system psi A B is not psi A tensor psi B or phi B. Okay, that means you are not able to write individual state of particle A and particle B. Then this state is called entangled state. If you can write psi A tensor phi B, then there is not an entangled state. So entangled state is negation of this tensor product state. Okay, so what happens is then that individual particles are not independent. That means if your composite system is in an entangled state, then it is not possible for you to associate an individual pure wave function to each of these subsystems. Okay. Some of you might be knowing that if you have an entangled state and if you want to define the what is state of this other particle, you have to do a partial trace. You have to trace out this other particle. Then what you will have is a mixed state, not a pure state. And these kind of state are linked in a strongest possible way, even if they are far apart. That means if I prepare an entangled state in my lab and keep one particle and send other particle to your lab could be in Delhi or could be in Bombay or maybe in some other part of the world, still they will be in an entangled state. There will be a kind of strong correlation. And this entanglement is another weirdest feature that you see in quantum world. And now we understand how to use these to do imaging tasks, which are otherwise impossible in classical world. And these entangled state display many strange things. One is instantaneous correlation, that is measuring one particle's property, like spin polarization, instantly determine the other particle's property, even if they're far apart. And Einstein's view was there is some kind of spooky action going on, and that challenge local realism. But nevertheless, you will not be able to use these entangled state for faster than light communication. So what that tells you that correlations are real, but cannot use those correlations to transmit usable information. And now we know that these are the basis for quantum technology, like quantum computing, quantum communication, quantum cryptography, and many other things. And entangled particles behave as a single system, so the whole is more than the sum of its parts. This is one of the famous quotation by Schrodinger in 1935. And this kind of state, as I said a little earlier, they display so-called quantum non-locality. So what is that non-locality? And basically that's the work of John Bell, who tried to prove that no local hidden variable theory can reproduce all predictions of quantum theory, quantum mechanics. That means your non-locality is a fundamental feature of nature. And the first confirmation came by experts group in 1982. And later on, many others also did, like Zeilinger and others. And in fact, expert Zeilinger, they received Nobel Prize, in 2022 for this entanglement, Bell test and other quantum teleportation, other things also. So quantum mechanics forces us to abandon the classical picture of validity. That is the essential lesson we learn from John Bell's work. Now there is something also interesting about quantum information, and that tells you how distinct, how different they are from classical information. So here I will try to highlight how quantum bits are, how they maintain the privacy. Okay. So first, notice that quantum state contains vast amount of information. Okay. Now, for an external observer, if you want to try to reveal what is inside, they don't reveal all the information. Okay. Why this is so? That is because of this, the limitation imposed by quantum mechanics. So think of the following situation. Suppose I have a quantum state, single qubit or single spin of particle, like alpha up, beta down. Okay. And I don't know what is alpha and beta, and I give a single copy of this spin half particle or a single qubit. And now I ask you the following question: can you determine the state? That is, can you determine what is alpha and beta? The answer is no. You need infinite number of copies of this quantum state to determine this alpha and beta. Because to determine alpha beta, you have to measure these Pauli matrices sigma x or sigma y, sigma x or sigma z, or sigma y or sigma z. By measuring these two observables, you can measure theta and phi, and that will determine what is alpha and beta. Because you know your quantum bit you can represent as a point on the surface of the Bloch sphere, and alpha is like cos theta by 2, and beta is like sin theta by 2 exponential times I phi. So theta phi you can determine by measuring this average of sigma x and sigma z. Okay. And you know that in quantum mechanics, to determine average of any physical quantity, you need infinite number of copies. From single copy, you will not be able to determine what is alpha and beta. That basically gets translated to the statement that from a single qubit, by doing measurement, you can extract only one bit of information. You will never be able to obtain all the information about alpha and beta. So that is the beauty of quantum mechanics, that given a single copy, given a single quantum bit, given a single spin of particle or single photon, nobody can determine what is there inside the quantum bit. Okay. And that has a lot of implication, like no cloning theorem, no deleting theorem, all these things, all the limitations that you see basically can be traced to this fact that you are trying to manipulate the inaccessible information, okay, from external, from outside. Okay. So the first no-go theorem is something called no cloning theorem, which was proved by Reuters and Jurek in 1982. That tells you that it is impossible to make a copy of unknown quantum bit or qubit. In 2000, we tried to prove, myself and Brownstein, we tried to prove that given two copy, it is impossible to delete one from two identical copies of unknown qubit. And in 2007, we tried to prove something called no hiding theorem. It is to do with the notion of information loss. Okay, suppose you have a quantum bit and something happens to your qubit, and at the end you lose all the information. That means to give a simple example, start with a single qubit like alpha up plus beta down, or alpha 0 plus beta 1, and I apply some I mean in quantum information language we say we apply some quantum channel which transform this quantum state to, say, completely random state like I by 2. I means identity matrix I by 2. Okay. So that has no information about alpha and beta. Now you can ask question, what happens to alpha and beta? Where it has gone? Okay. Is it really lost, or something happens to alpha and beta? Then you can show, you can prove that if information is lost, then it simply moves to another subsystem in a larger Hilbert space, and it cannot remain in the correlation between this original system and anything else in the universe. That means you cannot hide in the correlation. And that, in some sense, is trying to prove that information is ultimately conserved quantity. That means if you lose from here, it must be sitting in some corner of this universe. Okay. Now, in 2018, we proved something called no masking theorem, which tells you slightly different notion about how to store information in correlation. Typically, we imagine that information is stored only in physical body, but can we store information only in the entanglement or quantum correlation, so that the not here or not here? Okay, that means you put a mask on the system 1, system 2, don't see anything here, but they somehow remains in the correlation. Then we prove that no, it is not allowed to do that. So you cannot mask information. That is why you call no masking theorem. So here is a schematic way to what I said. So the no cloning theorem is a hypothetical device which takes input and you have a machine and that produces two copies psi and psi. This is again not allowed. Now in non-relation, you have two input psi psi, and you build a machine so that at the end you have psi and 0. This is not allowed again. In no heading, you have something and something happens to the system, and then at the end you lose everything. But then you can show that the lost information can be simply get transferred to some part of the environment. And in no heading, in no masking, we have input and you map to a larger system so that individual parts like 1 and 2, the density matrix rho A, rho B, they don't have any information about psi. That somehow psi is sitting in the correlation. Is it possible? Then again, we show that not possible to keep only in the correlation. Okay. So these results try to highlight the larger difference between classical and quantum information. Okay. How different your quantum from classical information. And also they have deep implication for quantum computing, quantum information, quantum communication, and technology also. Because you can the quantum cryptography is largely based on the no cloning theorem, and in quantum error correction, you can find the application of no hiding theorem and so on. Now, the larger subject of quantum information is how well you can store and process information and transfer information using principle of quantum mechanics. And what you do is you use features like superposition, entanglement, non-locality. You can exploit them, these features for particular applications or for doing imaging tasks which are impossible otherwise in classical world. Okay, now coming to quantum communication, typically this is setting, you have a person Alice, you have somebody called Bob, and they share a quantum channel, means before starting the protocol, they already have access to the entangled particle. That means there is some source here, and that source emitted two particle 1 and 2, and one particle goes to Alice, other particle goes to Bob. So this quantum channel is basically an entangled channel. And they also have access to classical channel. Classical channel could be your ordinary telephone line or internet or anything you can think of. And Alice will do something to her particle and this entangled pair, half of the entangled pair. Something means whatever is allowed within quantum mechanics, like unitary or measurement. Bob will also do something that is allowed within quantum mechanics. At the end, they will achieve something. Okay. Now, in quantum communication, many things have been discovered, starting from teleportation to remote state preparation, quantum key distribution, quantum internet, and many things. So teleportation is one of the beautiful things. You will see, but let me tell you what exactly is teleportation. In teleportation, basically, you see that there is a device and somebody enters and he presses a button and disappears from here and appears in some other planet. Okay. Now, before 1993, if you ask this question, can you teleport a quantum state? The answer was thought to be no. Okay. Why it is so? Because to teleport a quantum system, what you would do? Okay, you would scan the information and then you will send all the scan information to some distant location, and distant location will have some raw material already present there. And then once at the other end you receive the information, there will be some device and that will reconstruct the object from this received information. That would amount to some kind of teleportation. But then we know that given a single quantum state, it is not possible for you to scan or read all the information. Already we know that this is not allowed. Now we may think that, okay, let me make copy. I will make infinite number of copies and then I try to read the information. But then by no cloning theorem, we cannot do that. Okay. So because of these, people thought that this is not possible to do quantum teleportation. But then In 1993, Charles Bennett, Gilles Brassard, and few others, the 6 scientists involved in that paper, they came up with the idea that if you use entangled state, then you can do quantum teleportation. And that is one of the most profound discovery in quantum information, and one of the most beautiful equation that you will see is this equation that I displayed here. This equation tells you everything about quantum teleportation. I'm not going to explain this. I just thought I will just flash it. That how simple and beautiful it is because of the simplicity. So let me tell you how this setup looks like. So you have Alice and Bob, and there is somebody, and somebody comes and gives a state single copy of a quantum state like qubit to Alice, and Alice's job is to teleport this to Bob. Okay. Now they have this entangled channel, basically a spin singlet or one of the Bell state. If you don't know Bell state, don't worry. Basically, any state you can think of like 0 0 plus 1 1 or 0 0 minus 1 1 or 0 1 plus 1 0 or 1 0 0 1 minus 1 0. Any one of 4 state you can choose, and you can share beforehand before starting the protocol. Okay, that is the entangled channel. Now what Alice will do is she will take this input and take this one particle and do some joint measurement called Bell measurement, and then she will send only 2 classical bits to Bob, and Bob will apply a local rotation like sigma x, sigma y, sigma z, and then the state of this Bob's particle will get transformed miraculously to the state psi that was given to Alice. Okay, and this psi does not go through this channel, does not go to this channel, but somehow disappears from here and appears here. That is the exact dictionary meaning of teleportation. You destroy the object in one location and recreate the same object at a distant location. And how do you see that? That you see simply by looking at this equation. So this is psi, the input here, and this is the pure state, basically this 5 plus. 5 plus is basically 1 over up to normalization, it is basically 0 0 plus 1 1. Then what you do is you just rewrite, so write psi as alpha 0 plus beta 1, and write this as 0 0 plus 1 1 up to 1 over square root of 2 and so on. And then you rewrite the particle 1 and 2. This is, suppose you call particle 1, this is 2 and 3. Particle 1 and 2, you rewrite in the Bell basis, I just told you, like 0 0 plus minus 1 1 and 0 1 plus minus 1 0. In those basis, you rewrite, and then this EY basically or sigma x, sigma y, sigma z or identity. Just rewriting this equation beautifully captures quantum teleportation. Why this is so? Because Alice will do the Bell measurement, and these are 4 orthogonal bases. Suppose she gets B1, okay? Then the state will collapse to U1 times psi. If it is B2, this will collapse to U2 times psi. If it is B3, it will collapse to U3 times psi. If it is B4, it will collapse to U4 times psi. Now there are 4 distinct outcomes, and log base 2 times 4 is 2 classical bits. You will send 2 classical bits, and then Bob will do the correction because the state that appears here is Ui times psi. Okay, so Bob will do Ui dagger, that is sigma. Basically, this sigma x, sigma y, sigma z. So she will apply the correction like sigma x, sigma y, sigma z, and sigma x square is identity, sigma y square identity, and so on. So that means at the end, state psi will appear here. The single equation beautifully captures the quantum teleportation protocol. Okay, and this is one of the most profound, most simplest, and remarkable equation in quantum information. Okay, now in 1997, soon after this proposal, the proposal came in 1993. So just 4 years after this, this group in Austria, they did the first experiment. They teleported a single photon over few meter distance, and here you see Charles Bennett here and Gilles Brassard here, and Miluter and Richard Joja, and this is I don't know how to spell this person here, and this is Yasser Perez. Okay, and here you see this Anton Jellinger group in Austria. So the person standing here is Anton Jellinger, and this is Jeff Pan, who is now leading the China's quantum computing quantum technology mission, and I think these other four are his postdocs at the time. So they did the first experiment, and in Nobel Prize citation, this work is also mentioned. So Andre Delegate received Nobel Prize for not only Bell violation but also this quantum teleportation also. And by the way, Charles Bennett and Julius Brassard, just few days back, they received this Alan Turing Award in computer science, which is equivalent of Nobel Prize in computer science for their, for their contribution to quantum information science and for the discovery of quantum cryptography, like Bennett-Brassard protocol, BB80 protocol, and so on. Okay, so over last several years, a lot of progress has been made. So latest record-breaking quantum teleportation has happened by Chinese group over about 1,400 kilometer distance using low Earth orbit satellite and ground observatory. This is the record distance they have achieved. Now the other protocol is remote state preparation, which I proposed in 1999 and it was published in 2000. This is not exactly quantum teleportation, but basically it is similar to teleportation, but it is much simpler and you don't need more complicated Bell state measurement. It is just single particle measurement, and using entangled channel, you can remotely prepare a quantum state. The goal is, at least you want to prepare a known quantum state above place without physically sending the qubit. And what you can do is you can use entangled state local operation and classical communication of just one bit and prepare a state of head choice. Okay, and this has been also done by experimental done by many groups. So the scheme looks like this. So Alice and Bob, they shared this entangled channel, and Alice has something in her mind, and depending on her choice, she will do a rotation on this particle and then do a measurement and send only one classical bit, and then Bob will do some local correction and get the state size that was in Alice's mind. Okay, so again, imagine that simple analogy. So suppose Alice and Bob are friends, okay, and Alice want to prepare a new dish for Bob. So what she can do? Either she can prepare the dish in her kitchen and parcel it and courier it to Bob, and Bob will enjoy the dish, or Alice can make a phone call to Bob and then tell, okay, you do this, do this, do this, and Bob can prepare the dish in his kitchen. Okay, but then all the tasks will will be costly because in first scenario she had to send by courier, that will be expensive, and in second scenario she had to do a lot of telephone call, so a lot of classical information had to be sent from Alice to Bob. But here quantum entanglement helps you to prepare a state of a choice by sending only one classical bit, by using only one entangled pair. Okay, so this is the idea of remote state preparation. Now, in quantum communication, a lot of other things has happened over the last 30-40 years. One important thing is quantum key distribution. That basically ensures unhackable key distribution, and no cloning principle helps you to prevent eavesdropper from copying quantum state without detection. And the first idea came by Bennett-Brassard, for which they received the Turing Award, and soon after BBM 92, Agate protocol also came for secure communication. And this quantum key distribution helps you to eavesdropper detection, because any interception disrupts the quantum state, and that will give alert to parties involved, and they will abort the protocol. Quantum internet is another promising direction proposed by Jeff Kimball in 2008. So what you do is you create different nodes and you store information and process and encode, process, store in those quantum nodes, and quantum nodes are connected by quantum channel that can transport qubits from site to site. For transporting qubits from site to site, you can use teleportation, or you can use remote preparation and other things also. And you can distribute entanglement over the entire network, and that would finally lead to quantum internet. You can download entanglement, or you can download qubit, and use it for computation or communication and send it back. Then some other user can use it later on. So this is still very futuristic, but but very promising. Okay, I will not have much time, but I will just try to tell you what is going on in quantum sensing direction. So in quantum sensing, you use quantum phenomena like superposition, entanglement, and squeezing to measure physical quantity with sensitivity far beyond classical limit. And you get some new advantage, Heisenberg limited precision, entanglement enhanced measurement, quantum coherence for long interaction time, and so on. And that will lead to real-world application in emerging areas like biomedical, non-invasive brain, heart magnetic imaging, navigation like quantum accelerometer or gyroscopes, geophysical applications like underground resource detection or earthquake monitoring, and even fundamental physics. So quantum technology basically is a quite vast area. So you have the quantum computer, quantum processor, quantum software, quantum communication involves QKD, teleportation, remote state operation, quantum random number generation, quantum secure network, quantum internet. In quantum sensor and metrology, you have atomic clock, quantum gravimeter, quantum magnetometer, and so on. Quantum material basically involves how to design quantum hardware for quantum computers and building new devices for quantum sensor and so on, like quantum dot, quantum simulators. A lot of things are happening over last 10-20 years. So quantum technology is, or quantum computing, quantum information science is truly an interdisciplinary area where you need expertise from quantum theory, you need from computer science, you need from engineering, from information theory, from communication, cryptography, and many things, many more, expertise. So that is why in this area you will see people working, those who are working not just from physics area, but from diverse area of science and so on. Okay, so I'm almost done now. So let me try to summarize what I said. So quantum information technology is fundamentally different than classical information technology, and quantum computers are very promising devices, and they can perform certain computational tasks much more faster than the classical counterpart. And I try to tell you that quantum information is secure at a more fundamental level due to no cloning, no deleting, and all these no adding theorems and so on. And quantum communication is again very promising direction. And to achieve something in quantum communication, you need entanglement, and that is why this is a very useful resource. And the next revolution you will see, or already we are witnessing, and even we will see more in coming years, and that will be due to quantum computing, quantum communication, and quantum information technology. Okay, with that, I thank you for your attention. And now, if you have any question, I will be happy to take now.
Yeah, thank you for this very good talk. And now I request Subhan to take rest of the session, question answer session. Professor Subhan, can you hear me?
Yeah, I can hear you. So, is there any question from the audience?
So I see one question that is there any scope of quantum computing in India in the near future? I think it is by Deepak Shutar.
Yeah, already, you mean actually building quantum computer? Yeah, so there are a lot of progress happening. So like some of you might be knowing that TIFR, in collaboration with the TCS, they built 6-qubit processor, and this private startup QPI AI, they have bought some 26-qubit processor and so on. So already two startups are investing and building quantum computer in India now. Yeah.
Okay, so the next question, as I say, for making stable quantum computing, we need quantum system that have large energy difference between the ground state and the first energy state. Is it because of thermal noise? It is asked by Nitesh.
Yeah, so it could be
Yes.
thermal, it could be interaction due to environment, or could be interqubit interaction. So there are many things that drives the decoherence and try to destabilize.
Someone is asking, Ayush, asking, Sir, Alice information can I can't read it properly. Can both information can Ayush, can you elaborate it?
Maybe he can ask. Can you ask yourself, Ayush? Or they cannot ask?
We can make unmute him.
At least information can both information get both. Not clear what he's saying. So
Ayush, you can ask directly.
Hello.
yeah.
Yes, sir. Yes, sir. I want to ask if Alice have two information, U and M. Then Bob will get only one information. Can it will be possible that both the U and M will be get to Bob?
No, Alice in case of teleportation, Alice had to get Alice had to send 4 classical bit. Sorry, 2 classical bit. Okay, because she's getting 4 distinct outcome. Okay, she's measuring. She performing bell state measurement on 2 qubit. One is input and one is the half of the entangled pair. Okay, so she doing measurement on 2 qubit. 2 qubit means the Hilbert space is 2 times 2, so 4 dimension. That means she will get 4 distinct orthogonal outcome. Okay, those 4 distinct outcomes will be encoded in 2 classical bit, and then she will send 2 classical bit. So either 00 or 01 or 1011. Okay, and then depending on the classical information, Bob will do the correction, and then the state will be teleported.
Sir, actually, quantum thing is very fascinating to me. In my MSc lecture, I will also publish something like quantum batteries, which is very sufficient for our, which is very good for lithium. Means it can be beat a lithium battery. So, can you suggest something? So, can I work for quantum battery?
Quantum battery is another promising direction where a lot of proposals have been made how to store information with single qubit, 2 qubit, multiple qubit, and extract energy efficiently, and so on. So a lot of work is going on quantum battery. Yes, that is a very active area of research. Yeah.
Sir, I will write something about in my dissertation also. I will combine quantum battery with piezoelectric material, but I have very less information about quantum. So, what can I do next?
Yeah, so you send me a mail. I will send me a mail and let me know what you have done, and then I will suggest maybe what to do. Okay.
Yes, sir.
Okay. So, anyone else? Anyone else have any other question? So if not, I request Professor Subhan to conclude the session.
Yeah, thank you very much, Professor Poti, for this wonderful talk. And I hope all the students, those who are there, they very much benefited from it. And in future, we would like to invite you to our campus if you are free. So please, it would be a very good interaction with you. So thank you, all of you, for attending this session. Thank you very much.
And students, if you have any question, you can contact Professor Biswas and Das, or you can send to me also. Okay.
Okay, I think there is one question you may. Is there a fundamental thermodynamic limit to qubit stability?
Very good question, but fundamental limitation. I mean, in what exactly? I mean, it is a very generic question. You have to frame your question to some particular task. Okay, so if you do this task, what is the thermodynamic cost? Okay, is there any limitation? Okay, of course there are many limitations. Okay, so unless you specify the task, how can you say what is the limitation, right? So I mean, I want to do this and then I will write the question, what is the limitation due to thermodynamics? Okay, so there are yes, yeah.
I think
Okay.
this is
Like for example, the very famous thermodynamic limitation is so-called this Landau's eraser principle. To erase information, okay, you have to spend kT log 2 amount of energy. Like so if you reset your bit, okay, quantum bit or classical bit, you have to spend certain amount of energy. Okay, so that is thermodynamic limitation. Okay.
I think, okay, again, we got one more question. Let us address this. In quantum computing, as the number of qubit increases, does and how the system behavior shift from quantum to classical physics?
Yeah, so it is not always true that if you increase the number of qubit, your system will behave like classical. Okay, classical limit can arise on a different scenario. It can classical physics can arise in limit in case of h bar going to 0, or it can arise under some other system parameter. But just by increasing number of qubit, not necessary that system will reach classical physics. Okay, because quantum behavior, quantum coherence still can be maintained. Already you have seen, right? So people already built 6,000 number of qubit, 6,130. So that means quantum coherence is maintained with that many number of qubit. Okay. Of course, if you take to say in the theoretical limit, if you go to infinite number of qubit, then you will lead classical limit. Okay, but what I can tell you that this is still an active area of research. So how do you reach classical limit, and what really put the boundary between quantum and classical, that is still an open question. Yeah.
Someone again, can you briefly describe topological quantum computing?
Yeah, so in topological quantum computing, the main goal is to design your qubits using say Majorana qubit or some topological qubit, which will have inbuilt fault tolerance. That means if you do some disturbance to your quantum system, if you change some external parameter, if you change some control parameter and so on, your qubit coherence or qubit entanglement and so on, they will not be deteriorated. So topological qubit are very promising to be inbuilt, to face the inbuilt fault tolerance. So that's the main goal.
Okay, so thank you again for taking this question after the formal ending of the talk. So
Yeah.
now I think we can close the session, and
Okay.
thank you again, and hopefully
Okay,
we'll
thank you all.
meet again.
Yeah. Thank you. Yes.
Okay, bye.
Bye.